Hello everyone, I'm Wei Zhang from Shanghai Jiaotong University, and today I will be presenting URSA, our newly proposed precise capacity planning and fair scheduling system for public clouds, which automatically suggests the just enough resource specification for database workloads while meeting their performance requirements. It proves that URSA significantly improves resource utilization on the cloud and reduces the performance unfairness between co-located workloads. My presentation will include these 4 parts. First, some background information and motivation about URSA. Second, the design methodology of our work. Third, the evaluations and some results we've got. At the end, we will summarize the URSA. We first introduce some background information and motivation of our work. Platform as a service, which we call PaaS, is a type of cloud computing in which a service provider delivers a platform to tenants. Within the PaaS category, the fastest growing segment is the database platform as a service, dbPaas. The cloud vendors offer a variety of database products, such as Amazon Relational Database Service and Alibaba RDS. Most often, tenants rent powerful cloud instances to ensure the good performance of their database workloads empirically. However, the empirical method often results in the excessive purchase of resources, invalidating the low price benefit of cloud computing. In the right figure, we present a resource utilization analysis for a production cluster at Twitter with thousands of servers over 1 month. From the figure, we can see that the actual CPU and memory utilization is consistently below 20%. However, the cloud users apply for up to 5 times resources than their actual demands. This kind of over-provisioned reservations results in the underutilization in data center. That's why we need capacity planning in data center. Capacity planning identifies the smallest resource specification, such as core number, memory size, for implication while its performance requirements can be satisfied. Obviously, there is an existing important problem in capacity planning: how to get a balance between the resource utilization and the performance goal of the workloads. Actually, this problem has been resolved for private data center, and there are some related prior work, for example, the Bubble series and the Corsa series. However, to predict an appropriate specification for the coming workloads, prior works often provide the target application online for many times with various resource specification. Extensive profiling is not applicable for all workloads in public clouds due to privacy problems, which means that the tenants may not want to expose their database level statistics, and it brings new challenges. So what is new challenges? As to pool utilization, we need to identify the most cost-efficient specification that satisfies performance requirement. A straightforward method is profiling the workload with all specifications. Heuristic search is a solution to reduce the number of tries needed to identify the required specifications. However, it can get stuck in local optima, and the large search space results in the long profiling time. For each try, we need to run workloads and collect the performance data. Worse, it's not practical to rely on the profile-based method in public clouds where normal tenants care about privacy problem. In addition, when the database workloads are co-located, they suffer from performance unfairness. To investigate this problem, we run the 55 workloads with the same specification and use Kubernetes to schedule them in our 7-node cluster. The bottom figure shows the performance of workloads normalized to its solo run performance. Observed from the figure, some workloads are slowed down much worse than others. The main reason is the awareness of shared resource contention and pressure. Therefore, prior work is not applicable for public clouds. It's challenging to plan the capacity for workloads and keep fairness during the scheduling in public clouds. To this end, we propose URSA. Now let's talk about the methodology. To achieve this purpose, URSA should have the following abilities. First, URSA should be able to predict the scheduling surface of the target workload based on the low-level statistics and adjust the resource specification accordingly. Second, URSA should be able to quantify the interference pressure and its tolerance to the contention on shared resources using low-level statistics. Third, URSA should provide a contention-aware scheduling engine for database workloads across the cloud nodes. Now let's see how URSA solves the above problems. URSA is composed of an online capacity planner, a performance interference estimator, and a contention-aware scheduling engine. The figure shows the design overview of URSA that deploys a contention-aware scheduling engine at the cloud level, an online capacity planner, and a performance interference estimator on each node. The capacity planner precisely predicts the scheduling service of a workload and plans the appropriate resource specification for the workload. The interference estimator quantifies the pressure of a workload on the shared resources and its tolerance to the contention without relying on database-level information. The scheduling engine distributes the workloads across the clouds so that it would not suffer from serious slowdown due to shared resource contention. URSA performs capacity planning and scheduling for a new database workload W in 4 steps. First, W run along with the specification recommended by its owner for a short time and collects low-level statistics, hardware events level and OS level, required by the capacity planner. Second, based on an offline trained performance model and the collected statistics, the capacity planner predicts W's scheduling service. Third, carefully design the micro benchmarks that stress on the shared last level cache (LLC), memory bandwidth (I/O), and network bandwidth are co-located with W. By adjusting the micro benchmarks pressures, URSA quantifies W's pressure on various shared resources and its tolerance to the contention on shared resources. Last, based on the pressure and tolerance of W, the scheduling engine calculates the extent of W interference with the current active workloads on each node and allocates W to the node with enough hardware resources yet has the smallest interference. One key point in the capacity planner is selecting the low-level indicators for characterizing the scheduling characteristics of applications. We use lateral regression to identify the key features related to the workload's performance as shown in the table. The bottom figures show the flowchart of constructing the capacity planner. To construct the capacity planner, URSA provides the representative workloads with various specifications in a specific resource configuration region, collects each workload's performance scheduling surface and the identified low-level statistics in the table. Then we cluster these scheduling service into several clusters. Finally, we build a workload classifier for each standard specification in the region. Specifically, the training data for cluster is built as events cluster ID, where events is low-level statistics. Cluster ID is the clustering result of the application's scheduling service. When URSA performs capacity planning for an online workload W, the monitor thread collects the required low-level statistics of W, which are then passed to the classifier corresponding to the hardware specification of W. After W is classified to a workload cluster, the capacity planner returns an average scheduling surface of the cluster as a predicted scheduling surface of W. With the predicted performance scheduling surface, the capacity planner can use different planning policies to adjust the resource configuration accordingly. Next is interference estimator. The top figure shows shared resource contention between collocated workloads. Considering the shared resource contention while deploying the database workloads is useful for improving the performance fairness of the dbPaas cloud. Take the estimation of interference on LLC as an example. The interference estimator uses the low-level metric kilo-LLC misses per second (kMPS) to quantify the pressure on LLC. Specifically, we design a set of LLC stress programs with different pressure levels. URSA gradually reduces the size of its LLC quota until its kMPS rises by 10% compared to the case when it occupies all LLC. URSA records W's kMPS track as shown in the right figure and compares it with the kMPS tracks of the stress programs with different pressure levels. The pressure level of W on the LLC is quantified to be the pressure level of the stress programs that has the shortest distance to W. Meanwhile, the tolerance of W on the LLC contention is quantified as the number of cache ways when its kMPS rises by 10%. The contention-aware scheduling engine carefully places the workloads for enforcing the performance fairness caused by the unbalanced resource allocation, as shown in the top figure. For a common workload, scheduler will calculate a scheduler score, calculated in the left formula for each node. The scheduling engine considers both the contention of the shared resources and the resource usage at the same time. CS quantifies the contention score of the node, smaller is better, and RS quantifies the resource score of the node, smaller is better. For a node, RS is calculated to be the average percentage of the used CPUs and memory of the node. The engine schedules W to the nodes with the smallest scheduled score, so that W is scheduled to the node with the lighter contention and more free resources. Next, we will show our evaluation. We evaluate the effectiveness of URSA in the capacity planning and the contention-aware scheduling. We built a dbPaas cloud using 7 computer nodes. Table shows the configurations of each node. As to benchmarks, we generate database workloads by adjusting the configurations of 2 widely used workload generators. We evaluate the effectiveness of capacity planner in recommending appropriate hardware specifications in 2 scenarios. In the first scenario, a tenant finds its current specification does not satisfy the performance requirement and requests a higher but cost-efficient specification. In the second scenario, a tenant finds the performance of its workloads is satisfactory and requests a lower specification without hurting the current performance. We compare the specification recommended by URSA with the optimal ones. The optimal specification is identified by searching through all the possible resource specifications. The top figure shows the specification recommended by URSA and the optimal specification if the expected performance is 2 times and 3 times of the current performance. Observed from the figure, URSA recommends the optimal resource specification for 18 out of the 22 workloads. For the other workloads, the specification recommended by URSA has only 1 core or 2 GB memory more than the optimal ones. The figure also shows that all the workloads achieve the required performance improvement with the specification recommended by URSA. The bottom shows the specification recommended by URSA and the optimal specifications for the second scenario. Observed from the figure, for 11 workloads, the specification recommended by URSA reduces 43.6% cores and 16.5% memory compared with the original specification without degrading the original performance, and uses 7.7% more cores and 3.4% more memory than optimal specification. We also evaluate the effectiveness of the contention-aware scheduling engine. In this experiment, we collocate 56 database workloads that are randomly selected from the validation set. We compare URSA with state-of-art field scheduling strategy in Kubernetes. We run above experiments 10 times and report the result of each test. The top-level figure shows the total resource usage of 56 workloads recommended by URSA, normalized to their original specifications. Observed from the figure, URSA reduces 25.9% of cores, 53.4% of memory space consumption of workloads. The right picture shows the system-wide performance and unfairness when the workloads are scheduled with URSA normalized to the performance and unfairness scheduled with Kubernetes. URSA does not hurt the aggregated performance in all 10 tests compared with Kubernetes, and reduces the performance unfairness of workloads by 47.6% on average compared with Kubernetes. The improved fairness originates from elevating serious shared resource contention, and the overhead of URSA is pretty low. URSA identifies the appropriate node for a workload on our 7-node cloud in 0.12 ms using a single thread. In the end, let's give a conclusion. We hope to automatically suggest the just enough resource specification that fulfills the performance requirements of database workloads in public clouds. To achieve this purpose, we propose URSA, a capacity planning and field scheduling system. That's all. Thanks for your listening.